Got three talks. First up, we've got Charrier. No? Okay. I've been practicing my pronunciation, it's still terrible. So over to Julia.
Thank you, Richard. And first, of course, I would like to thank the organizers, both the organizers of the workshop and the organizers of the program. I'm very glad to be here. So I'm going to talk about quite theoretical numerical issue, which in my opinion can be quite useful to guide the choice of the numerical method and to understand what happens in terms of cost or speed of convergence. So I'm going to focus on the case of random PDEs, linear elliptic random PDEs with a lognormal type coefficient, and I'm going to motivate this kind of equation in the first part by talking about subsurface flow problems, and after that I'm going to present some numerical analysis issue. So actually this model is quite simple. So in this first slide you can see that is the deterministic model which consists, you want to describe subsurface flow. You have only one phase, so it can be water or oil, and this model consists simply in considering that you have only one physical quantity which really matters, which is the permeability, and we suppose this to be scalar to simplify. And what is permeability? If you have, we suppose that Darcy law applies. So Darcy law tells you that the speed of the flow is proportional to minus the gradient of the pressure, and the coefficient which appears here is A, so that's the permeability. What is permeability? It tells you what is the velocity of the flow when you know the gradient of the pressure. So now you use mass conservation and you have this quite simple PDE, and of course you have to add boundary condition, which depends on what you want to compute exactly. So because you have lack of data, you have to have in mind that to get data you need to dig some wells. So of course you don't have much data, and it's really also important in this kind of application is that you have really an important heterogeneity at very various scales. That's why we use random field stochastic models to take into account both the lack of data, that is to say the uncertainty, and the heterogeneity of the physical properties, hydrogeological properties. So the permeability is supposed to be a random function of a random parameter omega and of the spatial variable x. So you have a function of two variables. You can also see it as a random variable taking values in some functional space of x, which may be, for example, the space of continuous function. You suppose that A is the continuous function of the position x. So now you have the same PDEs as previously, but with randomness. So it's a set of deterministic PDE parameterized by a random parameter omega. So I think I'm going to, because, okay. So now I'm going to make some assumption to get theoretical results. So it's basically the same equation, but in order to simplify, I have put directly boundary condition and a second number f, and I suppose that f is in L2 to simplify. So first thing, for people who are not familiar with PDE, when you have this kind of PDE, we want the coefficient A to be bounded from above and below as a function of x. So for a fixed omega, you need A to be between some positive value A min and a sub-finite value A max. So I'm going to write the equation on the board. Because that's the equation I'm going to use for the whole talk. So that's on the domain and that's on the boundary of the domain. So now we have to choose a model for the permeability field, and that's where appear a log-normal law, because in the community of hydrogeology, it's quite a widely used model to model this quantity by the exponential of a Gaussian field, which is a log-normal field. And of course, it enables A to be positive, and it has been motivated by some numerical data and also by some physical arguments. So it's widely used, and it has some quite specific mathematical properties I'm going to explain later, and that's also why I'm focused on this kind of field. So we also suppose it to be homogeneous. So that means that the covariance function is supposed to be a function of the distance between x and y. And to simplify, I will suppose that the expected value of the Gaussian field is equal to 0, and then the law of G being determined by the expected value and the covariance, you have defined the law of your coefficient A. So it's enabled to modelize very heterogeneous field, and there is some picture here. And what's important is you really have this idea, you really get close to 0 and close to very high value. So it can go very close to 0 and very close to the infinity. So that's what you can see, because you have very very important range of value. So there are several quays, very small scales and some bigger. So now to define the law of G, it remains to determine the law of the covariance function. So I've given here two examples of covariance function. I would like to focus on these two examples, because I think it would be very interesting to show that these two choices. So I'm going to write on the okay, so the first one, which is quite widely used, is an exponential covariance function. So of course the covariance is a decreasing function, and the first choice is to show that it decreases like an exponential. So the covariance of the x1 is equal to sigma squared, which is the variance, times the exponential of the distance between x and y over L. So this constant, okay, no, sorry, it's lambda is my, yeah. So lambda is called the covariance length, and it tells you the length which gave you the scale at which the covariance decreases. So the second choice is Gaussian covariance. So I would like to insist on these two examples because they may seem quite similar when you look quickly, but actually when you're looking at all the mathematical property I'm going to study after that will be very different for these two examples. So it's the same, but with the square. Okay. So now I'm going to give some subdomain of application for this kind of model, which is, I say it, quite simple, but you are actually, that's more or less the model that Ahmed El-Sheikh presented on Monday for application to subsurface oil. But it can also be used to, that's why my application was to study groundwater pollution. And it can also be used for the storage of nuclear waste or that kind of thing. So, in order to finish to describe my problem from the application, I would like to insist on the quantity of interest, that's to say, what do you want to compute actually? So, on a theoretical point of view, you may want to compute the law of U. That would make sense when U, so the solution of the parameterized PDE, can be seen as a random variable taking value in some space, so H1, maybe. Should I recall what H1 is, or yes, no? It's a Sobolev spaces. It's functions which are in L2 with derivative in L2 too. So actually, in practice, you don't really want to compute the law. Computing the law is computing the expected values of some functional of U for a class of function of U, so for an infinite number of function phi, sorry. And on a practical point of view, you only need to compute this for one, maybe two specific function phi. So natural quantity of interest are the expected value of U, of the pressure. So it's a function of x. You may also want to know that's the mean value at each point. You also may want to compute the variance at each point. And other natural quantity of interest, you can want to compute the expected value of the maximum of or some mean value. You may want to compute the mean value of the outflow through a part of a boundary. That is quantity. So that all, I'm going to treat all this quantity of interest in my talk, but there also are, of course, more complicated quantities which require specific numerical methods, such as you may want to compute a failure probability, CDF, density, and also more complicated wear events, which is quite an important issue, and inverse problem, but its problem is a whole more complicated issue, which will be addressed in the fourth workshop. Okay, so now we want to compute the expected value of some function of U, which when we see U as a random variable taking value in H1, which is an infinite dimensional space. And actually, you can rewrite the problem as I will explain later how to do it, but you can see U as more or less as a function of an infinite number of parameters taking value is L1, 0, and what you want to do is to, when you want to compute this, is you want to do numerical integration for a function of an infinite number of variable and taking value in an infinite dimensional space. So in every numerical method, Is it better or no? No? Yes? So, in more or less, in every numerical method, you have to do spatial discretization. That means that you have to approximate this infinite H10, which is an infinite dimensional space, by a finite dimensional space. So, in more or less every numerical method, you have to deal with spatial discretization. That would be the first point I'm going to talk about. And then you have two strategies. You can keep a finite dimensional setting for the variable and use Monte Carlo type method, where you don't mind the dimension here. That's the first strategy. And the second one is to approximate the function as a function of a finite number of variables, and then to use more deterministic methods such as collocation or stochastic hierarchy, which in Monte Carlo case you are going to compute this at random points. In the second strategy you are going to compute to evaluate your function, so it's to solve a PDEs for deterministic points. So if you choose the second strategy, the convergence is very fast with respect to the number of points. If the solution is a smooth function, that's what Max Gunsberger talked about yesterday, you need to have some, the solution of the PDE U has to be a smooth function of the coefficient, the uncertain coefficient A. As explained, if U is analytical, you really have an exponential conversion actually. And but we are not actually, in most cases you have this kind of regularity for linear elliptic, linear parabolic PDE. For hyperbolic it's complicated, but it's okay for a large range of numerical methods. But another very important issue is that the cost is depends on the value of n, which is the dimension on which you integrate, and it increases rapidly with the dimension n. And if you use sparse grids or smart stuff, it's better than with vanilla tensored collocation, but it's what Max Gunsberger has called the curse of dimensionality. You always have this problem, and it was also in Ralph Smith's talk on Monday that you really have to choose a strategy, and to choose your strategy you have to know what is the dimensionality of your problem. So for low dimensionality you can choose strategy 2, but if the dimensionality is really high, you have to choose Monte Carlo type method. So it's really important to have an idea of what is the dimensionality deeply of my problem. So that's the question we will motivate the second part of the result I'm going to give now. So my first point was spatial discretization. I think you all have the intuition that the weight of the convergence of spatial discretization is linked to the regularity of the solution, the spatial regularity. So I'm going to give some results about the spatial regularity, and after that I'm going to deduce some spatial discretization results. So we have seen that the covariance is a function of x minus y. And I suppose that this function, okay. In all my talk, I'm going to suppose that this covariance function is a Lipschitz function of x minus y, which is the case in both my examples, because the norm is a Lipschitz function. So if you suppose the function k to be Lipschitz, for x fixed omega, you have that A, which is a log normal field, is a beta continuous order function of x for any beta lower than 1/2. So I'm going to give a few words about where it comes from. So first, we use the fact that G is Gaussian. So if you write what is this quantity, you can express it with the function, the correlation function, and with k, and you can bound it by using the fact that k is Lipschitz. So L is a Lipschitz constant, and then you can use the fact that g of x minus g of y is a mean-free Gaussian random variable. And as you know, if you have a mean-free Gaussian random variable, you can bound the moment of order p by a constant time, actually this is the moment of order 2p, by a constant times the variance, and the constant is independent of the choice of g. And you get this inequality. And why do we like this kind of inequality? Because you have a theorem which is called Kolmogorov continuity theorem, which tells you that if you have such kind of bound, you can deduce that your x, your random field, is order continuous for some exponent beta, which depend on the value here. So in our case, you get that it's all for any beta lower than this bound, and when you do when p goes to infinity, you get here 1/2. So basically, you have if k is Lipschitz, you have that for a fixed omega, a is a 1/2 order continuous function of x. So now I'm coming back to my two examples. So in the first one, you are Lipschitz k is it's a Lipschitz continuous function of x minus y, but you don't have more regularity. So the spatial regularity is 1/2 minus epsilon, but you can forget the order continuous. Whereas in the Gaussian covariance case, you have a lot more regularity because k is a very smooth function. This is a very smooth function of x minus y. So you have result. You can apply similar proof, and you get that the spatial regularity is C infinity. So you can see that there is a big difference in terms of spatial regularity. So in this case, A is not very smooth function. It's less than C1 function of x, whereas in this case it's very smooth function of x. Sorry. So that was the first issue, the spatial regularity. Now there is an issue which is very specific to log normal laws. I said previously that numerically you could see on the picture that there was value very close to 0 and very big values. So that means that you cannot bound A from above nor below uniformly with respect to omega. But you still have that, since we have some regularity with respect to x, so you are on the closed bounded domain, so you have some minimal value and maximal value. So for a fixed omega, it can be bounded by some from above by some constant A max which depend on omega, and from below by some constant A min which also depend on omega. So if you look at A. For a fixed x, it's a Gaussian, it's the exponential of the Gaussian, so it cannot be bounded neither from above nor below. So you never have one A max bounded or nor 1 over A min bounded. It's not in L infinity. So what does it mean? It means that you have to be careful when you're doing some numerical analysis and you try to look at the quantity, because if you can see this equation as a set of classical determinist PDE parameterized by some parameter omega. But the point is that if you try to apply classical estimate of numerical analysis, all the bounds you get, all the quantities that appear, they depend on omega, as they are not bounded as function of omega. So you have to be careful, because nothing is uniform or bounded with respect to omega, basically. So you have to track how things depend on omega. And now I'm going to explain how you can. It's not as bad as it could seem, because you don't have L infinity norm for this function of omega. But what you get is that it's not in L infinity, but it's in all the LP space for any finite p. Okay? So it's come for a theorem which is called Fernic's theorem, which basically, I think you all know that if you take a Gaussian random variable, it admits finite moment of order p for any finite p. And this theorem tells you that it's still the case if your random variable takes value into an infinite dimensional space. You just have to suppose that this space has some topological property. So how do you use this kind of result? I just want to show you this on a quite simple example. So it's classical in PDE and numerical analysis. You have, for a fixed omega, you have this bound. You want to bound the solution itself. So for a fixed omega, you have this bound. You can see that the bound depends on omega. So you want to have some bound which does not depend on omega. So you take the LP norm of this bound with respect to omega, and since 1 over A min belongs to LP for any finite p, you get a bound of u in this norm. So it's not a bound uniform with respect to omega. You integrate with respect to omega with some power p, which can be taken as big as you want. It just has to be finite. Okay, so that's to give you an idea of how do you use this result and how you deal with the fact that nothing is uniform with respect to omega. Okay, now we have the two ingredients to get bounds for the spatial discretization. These two ingredients being the spatial regularity and how to deal with unboundedness. So, I won't give all the details, but there are two things which are important. So, it gives you the bound. So, first thing is, as I said, your bounds are not uniform with respect to omega. They are also bound in LP of omega norm. So, it's LP H10, H10. So, just I'm going to explain on the two examples. So, in this case, you only have 1/2 Hölder regularity, which means your usual numerical method, you don't have the full order of convergence, which is in H1 norm. Here, in this case, you have only 1/2. So, the error sorry. I'm talking about, but basically you would have some similar result if you use it for finite element approximation. So I think Max Gunsberger explained quickly what our finite element is installed. So if for finite element approximation, but you may also consider, for example, in YD finite difference or finite volume numerical approximation. So UH is you only do for a fixed omega, you do spatial discretization by using finite elements. So when you do finite elements, you approximate your function H10 by some function in a finite dimensional subspace, which will be denoted by VH. So what does it mean? For example, in the 1D case, you approximate your function U by some function which is piecewise linear and continuous. So, and H is the mesh size. So you have the 0 here means that the value of U is 0 on the boundary. And so you have continuous piecewise linear function. So you approximated your function by some function in this space whose dimension is more or less 1 over h. So when you do this spatial discretization, the error is bounded by some constant times h to the power 1/2 minus epsilon, which comes from the regularity. So I have to give, so it's for H1 in H1 now, but it's not really important. Whereas in this case, you have basically it's another one method, so you expect the error to be like h, and that's what you get in this case, where you are smooth enough. Okay, that's basically what you have to understand of this result. Okay, so that's the proof. I won't give any detail, but the idea is the finite element error very classically can be bounded by the best approximation in the space VH up to some constant which depend on the coefficient and therefore on omega. And then to know how good is the approximation of U in my space VH, you need to know the regularity of U, and therefore you have to use some theorem we call elliptic regularity result. That is to say, why elliptic? Because it's an elliptic PDEs, and this kind of theorem tells you if you know the regularity of A and the regularity of F, what's the regularity of U? That's why they are called regularity theorem, because they give you the regularity of the solution as a function of the regularity of the coefficient. But here, we need what I call a personally precise result, because we need to know the regularity, but we also need to know here what's the constant. How is this norm? You know that this it's some space we gave you, it's Sobolev spaces, so it gives you the regularity, and the less S is bigger, the smoother the function is. And you also have to know how the bound of this quantity depends on omega, because as I said before, in this case, nothing is uniform with respect to omega. So you have to precise the classical result to know how the constant depends on omega. And you can see that actually it's polynomial function of basically A max and 1 over A min, and thanks to Hölder inequality, it's in all LP spaces. So that's what you have here. Your bond, you have some constant, but to get the constant, you have to integrate with respect to omega, but it's okay because of the result I gave previously. So you get the bound of 0. Okay. So now, so my first question was what is spatial regularity, and how can we bound the spatial discretization error. The second issue is how do you estimate the dimensionality of the randomness? Okay, so that's really for the second strategy, that's to say not for Monte Carlo type method, but for methods which are based on the approximation of the coefficient by a function of a finite number of random variables. So you are going to approximate A by a function an which depends on x and of n random variables. And then, instead of computing the solution u of this problem, you compute the solution of this problem, which is the same, but you have replaced a, the coefficient a, by the approximation an, which is on a function of n random variables. And then you can express the solution of the approximate problem here by a function un of the n random variables which were here. And of course, you compute the expected value of phi of un instead of the expected value of phi of u. And now you can rewrite it as a parameterized PDE problem of parameterized PDE with parameter in Rn, so a finite number, a parameter in a finite dimensional space of size n. And what you want to do basically is numerical integration on Rn. So you can use quadrature rule, and you have to combine this with spatial approximation, for example, through finite element approximation. So that's what basically is the simplest and basic version of stochastic collocation method. So when you do this, as I have explained before, if you do a vanilla collocation, the cost increase. The cost is like exponentially with n. It's better if you use, of course, if you use sparse grids. But you have really to know: can I have a good approximation of my solution for in a relatively small dimensional space? So, can I choose a quite small n and get a good approximation of u? So, as Max has also explained on yesterday, you can to get an approximation with this kind of random field. It's really natural to use Karun-Love expansion. So the idea is to write G as this infinite sum. So the lambda n, so Bn and Yn are normalized. So the decrease can be described by the value of the lambda n. So you get this decomposition by taking some eigenvalue of this operator. The lambda n is the eigenvalue of this operator, and the Bn are the associated eigenfunctions. So Max also explains that in the general case, you only have that the Yn are uncorrelated, but here it's the nice case because since G is a Gaussian field, you have that the Yn are not only uncorrelated but independent, which is quite that, and you also know that they are Gaussian random variables. So, and it's in L2 norm, it's the best multilinear approximation. So once you have this approximation, if you want to approximate G by a finite number of random variables, it's quite natural to truncate this sum. So, before going to this, so I have as I have explained, how, of course, it's very important to know how the lambda n decrease, because it will be the main issue to answer the question of the error committed when you truncate the theory. So coming back to my two favorite examples. So, actually, the main idea is the smoother the covariance is, the faster the eigenvalues decay. So, in this case, you have that the eigenvalues decay like 1/n squared. But, so that's the general result. But that's an asymptotic result that tells you how it behaves how it behaves when n goes to infinity. But for these applications, it's also important to have an idea of not only know the asymptotic behavior, because you can see that it is the same covariance function. It's an exponential covariance. I have only changed the value of the correlation length. And as you can see, the asymptotic behavior is the same, but if the correlation length is small, you have a plateau. And numerically, you can see that the size of the plateau is basically 1/L. So you have a for L equal to 0.01, the size of the plateau is 100. So it's really different from the case where there is no plateau. Okay. So in this case, we have explicit. If you take one decay or the one norm, you have explicit expression for the eigenvalue. So it's pretty nice. But in general case, you have some theorem which gives you a bound for the rate of decrease of the eigenvalue. So, for example, if the function is analytic, that's the case for the covariant. You can see that the decrease of the eigenvalue is much better because it's basically a minus constant n. You have, in this case, you have 1/squared, and in this case, you have exponential decrease. So it's because of the smoothness of the covariant kernel, it decreases really much faster. And actually, if you have seen this poster on Monday, in her poster, she presented some recent results, which improve the previous result on the decrease, but it's not in the analytic case. It's more in the for case like this. It gives you, I think, optimal weight. Okay, so now, of course, to approximate A, we truncate the Karhunen-Love expansion, and you compute the solution with the truncated sum. Okay, so that's the assumption. That's not really interesting. So what I wanted to do is to have a sharp estimate of, because first you have quite easily the error committed on A when you truncated, on G when you truncated the series, but I wanted to know what the resulting error, when I approximate A by G by Gn, what the resulting error on the solution of the PDE. How does the error on G impact the error on the solution of the PDE? So there are two ways to answer this question. The first one is looking by what in probability is called strong error. The idea is to compare, so strong error, I want to compare U of omega x and Un of omega x. That is to say, for a fixed omega, I want to compare U and the approximation. For a fixed omega, the same. Whereas the idea of weak error, which is actually more natural, because what do we want to compute? We want to compute low. We don't want to compute the value for a fixed omega. And we want to compare the law of, for example, I'm going to take the expected value, for example, at x, and the expected value of un at x. Okay, so my first bound is for the strong error. So I'm really, this bound is a bound of u minus un, and you compare for the same omega and the same x. So basically what you have to understand is bounded up to some constant by the remainder. You can forget the alpha, and it's the square root of the remainder of the series of the eigenvalue. So in this case, so if you have lambda n, which is more or less 1 over n squared, the remainder is 1 over n, and so the error, the strong error, is up to a constant, the square root of 1 over n. Whereas in this case, it's much better. You have the error committed decrease exponentially. It's not the same, not exactly this, but it's okay. Okay, so that's the strong error, which is basically the error you expect when you look at the problem, because it's the same error that you have on the up to constant that you have on the coefficient. So I think I'm going to skip the proof. So now if you look at weak errors in this case, so if you compare the law, for example, if you compute the expected value of u and the expected value of un, what's important is that we get rid of the square root here, which means that if the strong error is like 1 over the square root of n, if you compare simply the expected value, you have 1 over n, which is much better. And in this case, you have a constant 2 in the exponential. Okay, sorry. Okay, so that's what you need to have in math. We can get rid of the square root that you have in the strong error, and actually these weights are sharp. And okay, so it can be seen quite easily on this slide because you do some kind of formal Taylor expansion, and when you take the expected value, you can see that the violet term, they are when you take the mean, it's equal to 0, and that's why you get rid of this term, and you have the Rn because instead of the square root of Rn. So I just wanted to conclude with a simple numerical experiment where you can see that it's so in this case, so exponential covariance 1D, and you can see that if you look, it's the case of the I compare the expected value of u and un, so they are function of x, and you can see that actually even if you have this asymptotical weight, but I wanted to show that it's also important to know not only asymptotic behavior, because I have only changed the value so that the continuous line is the exact solution, and the other are for n equal to 1 or 10. So you can see that if the correction length is equal to 1, you don't have a plateau, and then you have a very good approximation with 10 terms, and even with 1 term is quite good. Whereas if you just change the correlation length, you have this plateau issue, and so the convergence is you have a plateau for the n first terms, and so you have to keep more term in the Caron-Love expansion. Okay, I think I'm already late, so thank you for your attention.
Thank you. Questions?
I want regarding your method. So you said it's for log-normal fields, but when I look at it, the main requirement was that almost every realization is Hölder continuous, wasn't it? Then it would
Yes.
work also for something else. Not
And the integrality properties, you have that you can generalize to the case it's when the norm of A in some norm A max and the Hölder norm of A and 1 over A min belong to all the LPs. That's the integrality issue. For the regularity issues, yes, indeed, you only need to have to know the spatial regularity, which is here, Hölder regularity. But the last point, the weak error, then you use the fact that you have some Gaussian random variable, so you have it depends on the case. You have to. I couldn't give really general assumptions. It would be not really interesting, but you have to check in each case. Sorry.
So concerning the dependence of the convergence rate of polynomial approximations on the truncation dimension, you can actually achieve dimension-independent convergence if you choose the coefficients in the right way. So you cannot use a generic sparse grid, but you have to choose the activated polynomial terms adaptively, so depending on the solution. But then actually the whole thing can become independent of the truncation dimension capital N, and it just depends on the decay of the Caron-Love terms actually.
You mean the error?
But the cost effectively and the error.
The cost?
So the convergence rate in terms of the total number of polynomial terms
Yes.
would become independent of this truncation dimension. If you choose the right...
But the cost can be chosen independent of the truncation.
Yeah, so essentially of course the dimension comes in, but it's dominated by the total number of terms that you need. And the effective rate really just depends on the decay rate of the Caron-Love terms. But that requires an adaptive choice.
He's talking about adaptive
Yes,
best n term approximation.
Okay.
I go back to the start of the talk. You motivated the whole talk by saying that geoscientists like these models of groundwater flow, particularly log-normal, and I guess you're saying they like the exponential covariance also.
Yes.
Just explain why. Why are they in love with these?
Because actually, I think simply the reason is that they don't want the realization to be smooth, because what they see is not smooth in their experiments. So I think one reason is that really want to have not this level of smoothness. That's one reason, and they have also references of some really ideological paper from the 80s where they show that it's relatively a good fit to data. Rob, you maybe.
No, you go ahead.
So there was, I think, general idea that it's kind of the smoothness they expect for, and also they have done some numerical comparison. I think so. I have some self-reference from.
So is it possible, you have a spectrum from very smooth to essentially very rough, that maybe you could go back to the geoscientists and say the thing you're picking is too rough, but you'll be able to compute more accurate results by using something which is a bit smoother. Is this feasible? Because there's a spectrum of covariance functions you could actually pick. These are the two extremes you have here. You could pick something which isn't as
yes, that you have the matter. I have just put some simple, but you have all the method class and you can use all the method class. But if you look at this paper in the 80s, it seems that they are more or less, for some ideologies, it can be the favorite one. But of course, there are all the method classes, which is you have all the range of regularity.
Just tend to follow their leaders. Well, if one guy writes a paper and says this is a good thing, they're sheep. They follow the big sheep.
There's, if I may make a comment, there's two aspects. So first of all, I was going to make a comment anyway. The one aspect that is not resolved by this question is that the main driving force for the high dimensionality is the correlation length. And even if you take smoother fields, you're going to have a short correlation length, and the dimensionality will always be high. The second point, I think I agree that for the spatial approximation, you can definitely get around the h to the half and say to the engineers, let's take my turn with nu equals 1. That will be a little bit smoother, and we can do the h convergence. That's my take. I agree with you on that, but I think it will not get rid of the dimensionality problem.
Fact.
I think that there certainly is there are a lot of papers in the geophysics community that advance the log normal and to a lesser extent the exponential, but it only covers a certain kind of subsurface flows, because a lot of subsurface flows, in fact most of them have layered media, you know, and obviously that's not layered media, so then you have to do something completely different. But there are cases like this in the geophysics community papers, and I work with a geophysicist who uses log normal all the time.
Last.
Yeah, so if I made a comment too, so when I talk to geophysicists, they all tell me of a nugget effect, no matter on what scale you are, which means realizations are not continuous. So maybe, I don't know, as a geophysicist here in the audience, maybe if she could comment on that.
A geophysicist.
Can I just one last? I think one point that you said that the strong conversions of your at the end is not as important as the weak. I think that's true for the pressure quantities of interest. But as soon as you do some transport or particle trajectories, then your results about the strong conversions are quite important. Because otherwise you can't prove anything about particle paths might be separated if you don't control the pathwise error. Is that correct? At least from a theoretical point of view, you need the strong error there.
I'm not sure if really the quantities such as the travel times really. I would say that it only depends on the law, but I'm not sure. I should do the computation.
Okay, so let's thank Julia again.